Very good evening. So today we will go ahead and do the process of task number 3. So the task number 3 is about scan cell insertion and the scan chain insertion. So what are we going to do in this particular task? So basically let's have an understanding, quick understanding on what is scan cell and what is scan chain. In any sequential system design, what we understand earlier is it's difficult to test any flip-flop. The reason behind that is because it's a sequential circuit, it retains the previous value. Unless I know the previous value, I may not be able to get, or I may not be able to predict what should be the next value, because the output is a function of like present state plus the previous output. So I may not be able to detect it, or I may not be able to say what will be my next state unless I know what was the previous output state, which means all the output of the flip-flop should be initializable externally. To do this, what we try to do is, like, we are trying to replace all the flip-flops with what you call it as a scan flip-flop. So this flip-flop, whatever I have here, normal flip-flop, this flip-flop is going to be replaced with scan flip-flop, this SFF. So that's the whole idea. This need to be done during the synthesis part itself. Previously you were aware of how the synthesis is being done. Now our objective is not about synthesis. Our plan is how are we going to replace the normal flip-flop with the scan flip-flop. To do that, how do we execute that in the Synopsys tool? That's the whole part of this. So this task consists of scan cell insertion and the scan chain insertion. To have a quick view on that, so typically a flip-flop which is available could be replaced by a scan flip-flop, something like this. A normal flip-flop, you might be aware of, there would be one clock signal followed by one D, and that could produce me Q to be the output. When it comes to scan flip-flop, it is expected to have few more signals which is being shown over here. That is the port SI, SE and SO. What are they? Basically, this is scan input, this is scan output, this is scan enable pin. So whenever I am replacing a flip-flop with a scan flip-flop, you could be aware of that their extra pins should need to be added towards all the flip-flop, which is basically scan enable, scan input and scan output. So what are we trying to do here? Say if I have 5 flip-flops, what I try to do is, like, through scan enable, I can feed in the data. Which is supposed to be led over here, and once the scan enable is being in on, so the scan input comes over here and it passes through the rose color line, which means I am chaining up all the flops, and externally I am feeding a value somewhere, like, say, suppose 0 1 0 1, something like this. When I feed this value, or the usual trend is you are expected to feed like 0 0 1 1 and 0 0 1 1. The reason for that we have already discussed. Like, when I give a pattern something very similar to 0 0 1 1, it is expected to go through all the transitions, like 1 to 0 transition, 0 to 0 transition, 0 to 1 transition, 1 to 1 transition. So the ideal pattern that need to be fed in for scan in is 0 0 1 1 pattern. So when I feed this much amount of data through scan in, what's going to happen is, for every clock cycle, the data which has been fed in moves over to the next, it moves from D to Q. For the second clock cycle, again this data move towards SO of the second flip-flop. Third clock cycle, this data move over here. So what I mean to say is, if I am having say 15 flops and this flip-flop has been chained up and converted to scan flip-flop, then to bring the desired value to each and every flop, you need to clock in a data, you need to feed a data and clock that for n number of clock cycle so as to make sure the output at each and every flip-flop is known to you. This is the basic idea of replacing a flip-flop with the scan flip-flop. What am I trying to do is, during the test mode, because you have two modes now. One, it need to work in functional mode, which is normally any flip-flop when it is supposed to work as a D flip-flop should work as it is like a flip-flop. When it is supposed to be tested, all this flip-flop need to be chained up to form scan chains, and they are supposed to be fed in with scan in, and for n number of clock cycle this n flip-flop will be fed in with the test data which you are trying to feed in, and that would be clocked for all the flip-flops and make sure all the flip-flop initial state is visible. So that makes sure that you are testing all the flops with the required, the value which you are feeding in and the value which you get out after n number of clock cycle going to be the scanned in as happened to be seen at the scanned out. So which really tells you that this flip-flop works fine. Or in turn now the sequential circuit becomes a combination circuit, because a sequential circuit is a combination of flop plus combo logic. Since the value of all this output are known to you, now you can apply any sort of ATPG algorithm for combo logic which we are using and try to test the stuck fall as we do for any combo logics. That's the whole idea. So what you could see here is the blue color line indicate that it is going to work in normal mode if it is not being set for combinational, if it is not being set for testing. The other case, it can be put in scan chain path mode. When I keep scan enable line to be 1, then this rose color line get enabled. Nowhere, this flop is no more going to act as a normal flip-flop, rather it is going to act like a shift register which is going to shift a sequence of value from one end to the other end. So this is the whole idea. So to understand much more, there are certain script tickle commands which has been used in our tickle script, what we use with Synopsys tool. Just let's see some of the basic tickle commands which is used for the basic DFT synthesis. So here, set DFT signal. This command is used for a specific DFT signal type, like to check for DRC with respect to scan chain insertion. Then report DFT signal command display the set of the signals that has been used for DFT. Say something like scan in, scan enable, scan out, all this. Then one more, create underscore test underscore protocol. This command is used to create test protocol based upon the user spec. So this command is also used during synthesis. This is basically to create a test protocol which is based on the spec which has been given by the customers. Next, DFT underscore DRC. This is to check the current design, is there any violation with respect to test. And set underscore scan under configuration. This is basically to specify the scan chain design, right? How many scan chains, all this you are trying to replace the flip-flop with the scan flip-flop. Then preview DFT, it is to preview the test points on the scan chain. And insert DFT, insert underscore DFT, this is used to add scan circuitry, that is scan based flip-flop, internal scan flip-flop. So this particular command will be used for inserting all these cancels. Then DFT underscore DRC coverage estimation. After these cancels has been inserted, this command is used to find out what is the test coverage without violating the DRC rule. So these are some of the basic commands which we will use for design compiler during compilation in this Synopsys. Right. So how are we going to source the tool, and what is the command basically we use for? The command that is used for synthesis basically DC underscore shell, the same, hyphen topo minus f. We are going to source actually this file, that is p synthesis tickle file. This file is already a script file which is available. We will look into it, what are the contents in that synthesis file, the script commands used there. And after using this, we are asking the tool to synthesize the design whatever which we given. So of course inside this tickle script we have mentioned what are these, what type of synthesis need to be done, what sort of scan need to be done. All this has been described over here. Next, minus output log, again this is used to store whatever the log file. So this is the user name, you can give any name, but this is the standard minus output underscore log underscore file. So basically this is the single command which is used for running this script in the DC shell, right? Okay. So actually speaking, if you have this p syn.tickle as well as the script file, and if you run this in the DC shell, then obviously this will do a scan based synthesis. Now what are we going to do is, let's see what is there in p synthesis.tickle. So to understand this, what I'm planning is, let's straight away open the tool and let's understand still more better. So let me increase the size of it. Yeah, to make it much more visible. Yeah, I believe now it could be fine. I'm just going to CD lab. So there is one more in that. I'm just going to the corresponding location where it is located. Synthesis. Yes. So let me list out all the files that are there. See, you have a number of files. What I'm going to show you here is, look at this. I have two files. One underscore con.stc. This is Synopsys Design constraint file. This we needed. And one more script file, p synthesis psyn.tickle. So these are the two files which we are interested in. Then we will see what is there in that. gedit psyn synthesis. I just open that. Let's see. Yeah. So this is the script file. Now let's quickly see what is there. Of course, the set path, set library. So these are the basic things that has been provided for any. I believe you would have gone through the synthesis, so I am not spending much more time on this. A detailed discussion was made on the synthesis. So we are defining all the libraries with link library, technology library, and in addition physical library. So all this library with the corresponding path has been given here. We are setting the reference, like reference library, design, then TLU plus library, which is basically for extracting RC, and the technology library, reference library, which is having like something very similar to left library in Cadence. So you have almost all this mapping library. So all the library description has been made. Then logical library setup, like their search path, link library, target library, all this has been given. Then physical library settings has also been, Milky Way library has been described. Now let's still go down. Now this is where which we need to look at. So first we are reading Verilog S298.v. This is basically a sequential circuit, benchmark circuit. So let me open that and see what is there. Yes, 298. So this is the benchmark file which is shown here. Now you could see this is a .v file. It would not have, I am just giving a .v file. It doesn't have any standard cell or any flip-flop. It has not been synthesized. It's directly the synthesizable code in .v file format. So you could see that always at passage of the clock, when you try to synthesize, this is definitely going to land up with a flop. So like this, the whole code is available here. I am just leaving out here. Now let's go back. So what we try to do here, we are reading this Verilog file. So for this task, I want you to take two such, apart from this sequential benchmark circuit, you need to take two more from the sequential library, benchmark libraries, take two and complete the process whatever we are going to do there, right? So the current design, basically the current design name and check design source underscore con.stc, right? So let's see what is there in underscore con.stc. So this you could see here we have, since this is basically going to work with the clock, we have defined the create a clock period 3, get all the ports, and we are describing all the latencies, uncertainties, input delay, max delay, min delay, because complete timing analysis is going to be performed and the flip-flop is going to play a major role. So we are trying to give the exact constraint, like what should be the minimum delay, what should be the maximum delay, what should be the port delay, what should be the setup delay, what should be the hold delay. All this has been prescribed over here. In fact, you can go ahead and change that also, right? So coming here, so we are sourcing this underscore con.stc, check timing we are making, set load, we are making the fan out load to be 1, the configuration, see, set scan configuration, what sort of scan cells which we try to, it is a multiplexer based flip-flop, which mean the normal flip-flop is going to have, replaced with the scan flip-flop. That's what we are trying to say. Compile ultra scan, this is the command which is used for performing the exact synthesis, scan synthesis, check design, set default strobe period, all this. Why period is 3? Because we are trying to launch a data at one end and capture at the other end. It is from flop to flop, so it's for a period of 3, like it's like one end you launch a data, the other end you go for capturing the data. The next thing, set DFT scan clock, you are just listing out, then reset signal, all this, create port. Now this is more important, we are creating a port of new port, because this would not have been there in your Verilog code, because this SI is the new port which is supposed to be created while you replace a normal flip-flop with a scan flip-flop. The direction for that is in, and set DFT signal view spec, port is SI, type scan data in. Similarly, SO scan output, scan data out, then scan enable, SE. So these three port need to be created for each and every scan chain which you are trying to make it. Say suppose if I'm having 100 flops and I am making 10 scan chain, like combining 10 flops in one chain. So for each and everything, for each and every chain, what you need to do is, like, you are supposed to go ahead and create SI, SO and scan enable, like SI1, SI2, SI3, like that 10, right? So this need to be repeated based upon the count of the scan chain. Next, see, this is the command which is used for creating a test protocol, create underscore test protocol, then DFT underscore DRC. This is to check is there any violations being made based upon the flop insertion, scan flop insertion. Test scan configuration. So this is also more important. Scan count is 1. This is what we mean is like how many scan chains are there. So if the scan chain is going to be too lengthy, then the time taken for testing it becomes a lengthy process. So under that case, it would be better if you have multiple scan chains in parallel, and this will reduce the scan flip-flop testing time drastically. So we are going to put them in parallel. So the scan count, no, it is given as 1. In the task which I want you to do is, I want you to take 2 sequential circuit. One sequential circuit you go with having scan chain 2, the other one you go with having scan chain 3. So that's how you need to make it. So 2 circuit, one with scan chain 2 and the other one is scan chain 3. Appropriately go and define this scan in, scan out and scan enable line. Okay, fine. So preview DFT, insert DFT. So you are inserting all the DFTs, then DFT underscore coverage estimate. This particular command is used to check whether the coverage has been done properly. Right. So you have given all the commands that need to be executed. Then you are trying to write certain things on your current directory. So write test protocol, because this test protocol is required for further on processing. So we store that in scan1.spf file. So let's see whether it is there. Scan1 already I have synthesized. So probably while you run the script, after the script has finished its computation, you will be getting like scan1.spf. So this SPF is the still format. This is standard test interchange language format. So this is basically used for all the exchange of testing conversion, this SPF, whenever you want to go with the scan insertion. So this follows this format, SPF format. So you store all that in something like what has been shown over here, this SPF file, which clearly indicate what sort of testing protocol that need to be followed. That's what it means here. Then you can also store that in DDC format. This is a Synopsys database format, .ddc format, that also you can say. Then write SDF time1.stc. See, this is basically to check the timing after inclusion of scan flip-flop. So let's try to open this scan1.sdf. So here what you could notice here is like the whole process, you will be having interconnect, and look at this, all the cells, right? So the normal flip-flops has been replaced by a scan. SDF refers the scan flip-flop. So all the scan flip-flop has been, normal flip-flop has been replaced with scan flip-flop with appropriate input-output signals, and for every flop that has been provided with setup time, hold time, all these details are available. So every cell which you have it, say this is one of the scan flip-flop which has been. So as for this particular design, 14 flops has been included, and all the 14 flops has the scan flip-flop has their own setup time and hold time to check for the timing violation if there is anything. So that has been mentioned over here. Apart from this, all the other instances has also been included. So let's go back. So this time is to check is there any path which violates the timing, this setup time and hold time violation. This is used to check it, right? Now write parasitic. Of course, this is for getting the exact timing. Only if you have this parasitic, you will be able to do that. Now look at here, write hierarchy format verilog output scan inserted.v, which mean the normal .v file which we have given has a normal flip-flop. After that, scan inserted.v file would have the scan flip-flop. You could also see here scan inserted.v. this is the file which we have written. After running it, see, look at here. So right from here, all the flops are scan flip-flop. So whatever this always block comes in, they have been replaced with the scan flip-flop. Otherwise, in a normal synthesis, this would have been landed with the normal flop. And you could also notice all the signals which we have mentioned there, SI, SC, and SO. All this would have been there for each and every flops. Now coming back, so scan inserted. Of course, since the synthesis is being made, you can get the area report, gate report, power report, timing report, so net report, the quality of routing report. This complete detail can be taken from the whatever report file which has been saved here. So basically, the area report changes, timing report changes when you go for this synthesis, because there is an area overhead of inserting this normal flip-flop with the scan flip-flop. So that could make a change. So that need to be taken into consideration. I believe you could understand. So whenever you are going with this sort of scan chain insertion, then automatically the area report, power report, timing report, everything is expected to change. And further on, that updated report need to be further taken forward. That's what it means here. Right. So that's it. I think we have gone through all this. Now directly we will go and run this command. So the command which we would like to run here is so as I said, it is a single command which you can go ahead and run this. I am just going here and let me run this command, that is dc underscore shell hyphen topo minus f p sy and synthesis dot tickle file. I am just running this. So it may take some time, so I want you to know back. So based upon the design complexity, this could also vary. So it keeps on running line by line. It start executing this commands. I want you to check for the want of time. Now you know what is being done by each and every command. Going to the script, I want you to take each and every line. I don't want you to run the script the whole thing, because you will find difficult to understand. Instead, I want you to take line by line, you feed in and see what is the corresponding change that has been brought in. Right. So let's start from here. What we try to understand, first of all the physical library, link library, target library, all those things have been said. So we will not worry about that. Coming here, so what is being said from all the library verification has been made, cell name, their corresponding physical library has been included. Fill cells, I think you would have come across this in the synthesis, so I'm just leaving that. Then TLU plus, that is also there for extraction, so it has been loaded. So right from here, all this are scan cells, right? G10 underscore reg, these are the registers. Now look at here. Now compilation has been completed, and the current design, all these details has been mentioned over here. Now scan load 1, scan configuration, multiplexer flip-flop, accepted, scan configuration for mode all DFT. It's a full scan, right? Ultra scan has been done, and coming over here, so all the details with respect to even RC extraction has been made. They were checking is there any violations with respect to that. Buffer trees, just to perform the timing analysis, it has been done. It says skipping remaining step due to the timing. go to finish. In fact, there won't be any timing violation in this. Uh, so you have made all this. So these are the pins that need to be created, like SI input, output, like this you are creating. All this for scan scan chain 1. So if you have multiple scan chain, that many number you need to create it. I want you to go back, refer some other material and see how to create multiple scan chain and how to have the report of that. So that's also going to be a part of the task which you are going to do with this particular one. So there are 14 sequential cells, which mean 14 flops, and they have been mentioned over here. And still, let's come down. Um, Insert DFT command is inserting the scan flip-flop. It sees is there any violation in that. So yeah, so after inserting the scan chain, it is just checking out is there any or what is the fault coverage. We have asked to perform the fault coverage. So deterministic like for 26, uncollapsed fault is 20, so total fault is 446. Then the fault coverage is 98. Again, this 20 left out fault, for that deterministic pattern has been generated and it gives me 100%. So only 426 has been initially found out using 4 out of 446, 20 were left out. Again, for the 20, deterministic test pattern has been generated, which will give me a fault coverage of 100%. Then what are the information like sorry, so you could get something like what are the faults, what are the types of fault. Uncollapsed stuck fault summary, that is detectable fault, possibly detected, undetected fault. So you have 568 which are basically detectable fault, right? ATPG untestable, there is nothing like that. So not detectable fault also nothing like that, since all the fault has been covered. So the fault coverage is 100%. So you are saving this in scan1.spf. Again, database format also, Synopsys database format also you are saving in, and the parasitic extraction has been reduced. Using this parasitic extraction, you are going to perform the timing analysis. The timing has been performed so what we see here is a positive slack of 1.01. So all the timings are met. So you don't have any, if at all, if you have any negative slack, then you need to go ahead and see what could be the way to bring the slack to a positive, such that the timing is being met. That you need to take care. So that's what we could see here. So complete detail you can have it. It's still you can also have the no the whole design in a GUI. So opening here, my best suggestion is you open here, then you go ahead and see line by line. You can go ahead and no you can go ahead and uh, no perform each and every command and see what is the corresponding changes. Say suppose this is the complete view of the whole code which we have taken, that is sequential circuit. You can just go ahead and see the flops that has been inserted here. So this flop, so this is basically a scan flip-flop. Can you see here? So this is D input for a normal functioning, scan input, scan enable. This is one clock net, and this is my queue. So all the flops would have been replaced with the scan flip-flop. So I believe this would have given you a clear understanding of what need to be done with this task, and yeah, the same thing has been said over here. Please go ahead and the script file I would have explained there. What are you expected to do in this particular task? So there are two parts in this. Part A, I want you to write a 6-bit counter with the passage clock, asynchronous reset, set, and synchronous initialization. Then go for synthesizing this. Go for DFT insertion and build a scan chain. Get area report, power report, timing report. Right? Then second part of this, you take two more circuit, benchmark circuit. This is one for writing a code. This is, you can directly go ahead and take two benchmark circuits, sequential circuits, and for one circuit you go with 2 scan chain, the other circuit you go with 3 scan chain. You repeat the same procedure and get the report. The report, what is expected in the report? Analyze Verilog code and test bench, synthesize script, synthesis schematic, timing, area, power report, DFT, DRC report. So all this need to be submitted. I believe this would be helpful for you. Hope we will meet in the next video, wherein I will go with the next task that need to be executed. Good luck. See you. Bye.